So yeah, thank everyone for attending. I wanted to since we have a small crowd, I kind of geared this talk for high level, for data scientists who might be interested in doing this type of work, or just to share what I've learned, but also to maybe people in finance. Or do we have any people from finance maybe interested in mining transaction data? I don't know. Or is it all like pure data scientists in the room? Yeah. So anyway, the goal of the presentation is really to just share a use case. I started working at Earnest about 5 months ago. I was hired as a data scientist there, and one of my first tasks at Earnest was really to start exploring our transaction data to see if we can begin to make sense of it and utilize it. The purpose of my talk tonight is to share some of what I've done with this data from a very high level. So I'll discuss the algorithms I used in minor detail, and then discuss how we can use them in subsequent modeling further down the road. So I mentioned neural nets really because that's what worked the best for this particular use case. When I first embarked on this, it wasn't really, we just had a lot of data. It was noisy, it was messy, there was no labels, and we were just trying to make sense of it. So we tried, clustering using various methods, using things like Levenshtein distance and stuff to make sense of the text data. But what ended up working was a rather simple architecture. And I'll talk about that in more detail. So my goal here is really just to have a high-level discussion or a presentation on, it could be for someone in finance who wants to leverage, maybe take away some of the stuff that I've learned and take it to their data science team, or for data scientists who maybe are doing similar type text analysis. So, I expect people here to have a little bit of knowledge about neural nets, know what a neuron is, and a loss function, things like that. But if you don't, feel free to ask or just email me or something afterward. So my goals today, I'll briefly talk about who we are at Earnest and what we're doing and how we're leveraging data science, just briefly. How can we take this transaction data, what is the data itself, and how can we use it to leverage, enhance our products and both build new products that are going to help the company but also help our clients. So a big part of the talk is really just around taking the transaction data and then encoding it. Basically converting it from a format of text into numbers. And then further modeling after that. So then I'll talk a little bit about next steps some of the stuff we're working on currently that's not necessarily, the results aren't really ready for presentation, but that we're working on. So who are we at Earnest? We're building basically a modern bank for the next generation. Our mission is to democratize access to high quality financial services. And we believe that we can interact with customers to build a synergistic relationship that benefits them and their financial status, as well as benefit the company. And the first step in this process is really to give college grads, this is just like a first iteration, is to go after people who don't have a lot of credit, and that's typically young people. It could potentially be somebody who's very old, but generally speaking, it's young people who have a college degree, and they don't really have any established credit, but we think that we can learn enough about them with modern data science to not just underwrite loans to them, but actually give them competitive loans. And we also have ideas around, or products around, interacting with them on a very regular basis. So it's not just a static credit report, give them an interest rate and sign the dotted line and that's it. We want to interact, we want to offer new products, we want to engage with them in a way that it improves their financial status. So the transaction data that I was tasked to work with, it's about, I think currently it's about maybe 100 million rows. It's about 1.5 terabytes of data, roughly. And the problem is there's no labels around it. It's noisy. And we want to be able to leverage it. We know that people are using these transactions. They're buying stuff with it. They're going to places, and we're getting signal of that. We know that they're taking out other loans. They're other financial products. They're spending their money in different ways. There's heterogeneity in how people behave. We feel that we can capture a lot of that in this transaction data. So, and the data, just so you know, is growing very, very rapidly, especially in the last month. We're really seeing it take off. So what is this data? Just briefly, when a customer comes to Earnest and they fill out an application, they are required to, when they undertake a loan, when they actually sign on and become a client, they're required to link their checking account, savings account if they have it, credit card accounts, what have you. The vast majority of the data is checking accounts, because most of our client base as of now is younger people. Most of them have a checking, maybe a savings, and maybe a credit card. Some of them actually have investment accounts, which is cool, but most of them it's just checking and savings. So the data, it consists of a timestamp, the amount of the transaction, and text. And the text is what I call the noisy data. It's very unstructured. We see text, for example, you see POS transaction, Anaheim, California, or you might see like transfer to XYZ account. And there's information often like financial institution. I apologize, guys, not sure. I forgot to turn off my hot corner there. Okay, so where was I? So, we get a lot of information. There's many rows of data, but the data, as you can see, can get messy. So we can see that, like, for example, we can see, like, for example, that there's a point of sale purchase at Anaheim, California, and it has an ID, blah, blah, 1, 2, 3, 4, 5. And we can see that a different user came along and for a different amount did something that looks like an ATM withdrawal. And ANHMA or MCA probably is Anaheim, California, but it would take a human to read that. And obviously it's the same store, it has the same ID. And a lot of transactions don't even have a store ID. They have other information that really doesn't mean much of anything. And then we have the exact same transaction from a different user, probably has a different financial institution, and we see ATM withdrawal in Anaheim, California, which is much clearer to read. So that's really the crux of the problem. The key is how do we make sense of that? And that's what I'll be talking about here. So some of the things we'd like to do with the data, I just want to mention this briefly so we know kind of what we're aiming toward. Making sense of the text is really just the first step in doing a lot of other things. So, we could look at free cash flow in the transaction data and make underwriting decisions, and we could look at history, and if we see red flags like derogatory transactions, such as payday loans, overdraft fees, things that might hint at financial distress. We could actually have like more sophisticated models, which is something we're working on currently, like change of state models. So state space modeling around, if somebody had a financial hiccup in the past and maybe their credit report doesn't look ideal, can we separate somebody who's just, in essence, a bad money manager, somebody who really just is bad with their money and we don't want to loan to them, versus somebody who maybe just had a hiccup, one-time event where they're generally good with their money, but there was a hiccup, something happened, they got sick. Sorry, I gotta watch that. Maybe something happened, that they got sick or there was some hiccup in their life that caused them to have a financial problem. Maybe it was a divorce, a death in the family, something serious that caused this to happen. But going forward, we have no reason to believe that they're not going to be a good customer. So those are the people we really want to try to capture. And we believe that the transaction data can give us some ground truth data to get closer to that. So just as a first pass to see if we could encode the information, we decided what we were going to do is basically vectorize the text in some way, either using like bag of words or traditional NLP methods, word2vec, and build an appropriate feature space with both the timestamp and the amount of the transaction, and then feed that. And if we can get label data, which is something we had to do manually, we literally sat and had a party and a competition, and you win a prize if you label the most transactions. We had a set of criteria. We did some evaluation on the labels themselves to make sure that the labels were actually of high quality, and they were actually of very excellent quality. We were happy about that. And it was a lot of fun to get everybody together and actually have a labeling party. That was fun. And then, so once we have labels, we ended up with about 22,000 labels. We tried out a handful of different, I say we, really, it was me doing all this. I tried a handful of different models, and I basically trained several versions of a feed-forward neural net. Basically a multi-layer perceptron is what it ended up effectively being. Gradient boosting and random forest, as well as a logistic regression model, which I think was a good baseline model. So just briefly, machine learning models need numbers. And typically, if you're parsing like Shakespeare or parsing, New York Times articles or Wikipedia, you have a lot of text. And the text is typically in English or perhaps another language, but it's written in such a way that it's in line with that language, and it's a little bit, there's a lot of methods that are in place to understand that. What we found with this particular data set is that it's just really messy. Traditional NLP methods just, for example, bag of words, where we take a vector and depending on the words in that particular row, we give it word counts to form a vector. This didn't work very well.
The data you're getting, they're your own customers' data.
Correct. They're our customers' data, nobody else's.
So then how do you get to know all those things, whether they have, financial stress,
yep,
and going for payday loan and all that kind of thing?
So when they link the account, it goes back pretty far.
Sorry?
When they link their account, we see historical data. Yeah. I know it seems almost Big Brother, but they're agreeing to do it to get to, because we can offer them a loan at a competitive rate where they wouldn't otherwise be able to do it. And we also feel that, some of the products we're building out right now are going to even extend that to more people. So we feel like we're going to offer a product that's good for people, and it's not just milking them. I mean, if you go to a poor neighborhood, you see check cashing places everywhere, and other financial products that are out there, especially the personal loan products that offer personal loans at just extremely hideous rates. And often these people are good to pay the money, but it doesn't show that on their credit report. So, there's an advantage to them to give us their data. Yeah.
And then all the ATM transaction, because it's coming from different banks' ATMs, that's why you get different type of text.
Yeah. So one thing we actually have not been able to discern is so we see across financial institutions, like if you're a Wells Fargo customer and I'm a Wells Fargo customer. And other people are we see consistencies across Wells Fargo's customers, but we also see that the encoding is also dependent on where the transaction takes place. And I'm not sure where that trade-off is, because this text data that's in our financial transactions, it comes from something called a payee name, which comes from one source, and the text is concatenated with other text that comes from another source. So it's a combination of all of the above, and it's messy. Yeah, but what we do have is text, and often we can make sense of it. And thank you for the question. So where was I here? So in order for bag of words to really work, we need lots of highly informative words. Like I mentioned, we want something like Wikipedia or New York Times articles, something where the text is clean. And what we have here is the opposite of that. We have very short sentences with often maybe just 4 or 5 words, at most 10 usually. And the words are often abbreviated or encoded, concatenated with no spaces in between, things like that. And that ends up making, a messy arrangement. But we do have the benefit that our data is specific to banking transactions. So like I mentioned a minute ago, we have a finite number of institutions, and those institutions tend to have patterns across that institution. So it means you might see a weird encoding, for example, transfer to, but you'll see that repeated across customers and across institutions. So because it exists and it happens enough and often enough, we can make sense of it. So it turns out that looking at co-occurrences actually works quite well. so you can imagine like transfer to and transfer to, and then some transaction account or some number. They co-occur in a similar manner. So you can see that the word to in transfer and to along with XFER would co-occur, and in a latent vector space, we would have a close vector. They would be considered similar. Same thing with payment to versus payment from. We could see that to and from would be highly informative in that regard. And because they would co-occur with various forms of the word payment, like PYMT or other PMT, whatever form, those co-occurrences basically build vectors for each of those occurrences of the word that are very similar. You can imagine using bag of words, that simply would not be the case. PMT would be treated differently, PYMT, and the actual proper spelling of the word payment. All of those would be treated differently. With the word vectorization model, it works actually quite well. And to that, I will speak a little more. So a lot of you who are familiar with NLP are probably already familiar with word vectorizations. At least you've heard of them, if not used them. I'm going to talk about both word2vec, which is actually a class of algorithms, several different algorithms, and the glove algorithm, which is one that I've really come to like. It's practically the same thing, it scales a lot better when you're dealing with pretty large data sets or distributed systems. So the word2vec, like I mentioned, is actually a class of several different algorithms. It predicts a word given what words are around it, or vice versa. It can predict the words around a word given the word, if that makes any sense. Martin Mull, a famous comedian, once said, writing about music is like dancing about architecture, so we're going to vectorize about words. It's an art. So this is a predictive algorithm. Like I said, it takes an input, and the input will be either a word, and it will predict the words around it, and that's called the skipgram method, or it will take the context. It'll take the words that are around a given word and try to predict the word. And both achieve pretty much the same goal of vectorizing the word. Explain that in just a moment. So I pulled this off the internet. I don't know if this is the best representation of how word2vec works, but basically each one of these inputs, so in the SIBO, that's continuous bag of words model, it takes the words that are around a given word, it vectorizes them with a one-hot encoding. So each one of those words is a one-hot encoded vector, with a huge vector of the size of the vocabulary. And it multiplies those by a weight matrix, which is the size of the vocabulary and the size of your latent dimension space. So each one of those basically gets a row in a matrix that's in the middle layer. So you could think of that as an n-dimensional neuron or neural net hidden layer. And then the output is an n-dimensional word vector. And a very similar process happens on the other side on skipgram. In this case, it's just a softmax. There's a loss function. You basically maximize the conditional probability to learn the word vectors. And in the other case, I guess it would be a multinomial distribution that you're working on there. So you can learn the posterior distribution of the words based on the softmax of the output layer. So I'm going to show this really quick for those of you that haven't seen this before. I think this is really cool, and I'm using capitals along with their countries to show how word2vec can capture semantic associations. And I'll talk briefly about how what that means for transaction data. So you can see that there's countries here and capitals there, and you could take Spain, for example, subtract Madrid, add Lisbon, and you get a vector that's pretty close to Portugal. Similarly, you could take Japan, subtract Tokyo, and add Ankara, and you get something that's pretty close to Turkey. It's kind of interesting that Japan and Turkey are both Altaic languages. I'm not sure. That might be a coincidence. It might not be. It's certainly not a coincidence that China, Russia, Japan are all linked together, because they co-occur with words like East, maybe Asia. Italy and Greece, Spain are going to co-occur with words like Mediterranean, Southern Europe, things like that. So those co-occurrences actually encode these words in this vector space in a way that is both semantically meaningful and, well, semantically meaningful for now. So you could imagine similarly to like, words like transfer to and payment to get also similar associations. And we found that to be the case. We found that like even weird encodings of like payday loan sources, where a lot of those places you've never heard of, it actually was able to capture them in a vector space, and we had a cluster of those, which was very interesting. I want to briefly talk about glove. For those of you that are not familiar with it, it's very similar to word2vec. I think it's practically the same thing if they're both implemented in the simplest sense. And what it does is it takes basically every word and calculates a PMI value for the co-occurrences of those words. And then what you do ultimately is you factor that matrix into a lower dimensional space, just like you would for non-negative matrix factorization or some other method. And what this does, though, it's because it's just counting words, and the way the algorithm is framed, it's really simple to implement this in Spark. It's literally like, a chunk of code, maybe 20 lines of code, and you can do this on huge amounts of data and get really good results. Because I ran my word2vec in Spark, I didn't use any negative sampling or subsampling. I just did a straight brute force approach to word2vec. I got nearly identical results. In fact, almost exact same results using this as I did with word2vec, using the skipgram method of word2vec. So this is just a brief summary of how we vectorize a document. First, we strip out all the number and character sequences that could represent account numbers, anything that's private information. We did some heuristics to try to get names out of there. It's not 100% accurate, but it works pretty well. We lowercase, we tokenize. And once we have a tokenized version, we can spit this into a word2vec model. So now we can celebrate. We're halfway there. We have vectorized our entire corpus. Now we have all of our text. It's in a vector space. Assuming the vector space has been done, like we've trained the model properly, we can probably use this for something more interesting. So what we ended up deciding to do, because most of our transaction data is actually retail, the vast majority of our young clients are, they're young. Most of their stuff is happening in their checking account, and they're swiping their card everywhere they go. So that's almost 50% of the data. It's like 40-something% of the data is retail transactions. So the first iteration was, let's just separate that out. Let's build a classifier that says this is a retail transaction or this is something else. So we first took a pass. We labeled 22,000 transactions, and we literally, like I said earlier, had a competition to do that. And I set up a range of models, as I mentioned earlier, logistic regression for a baseline. I feel like it's interpretable. It's easy to implement that. And then some boosting and ensemble methods. I'm sure most people here are probably familiar with these. And then the multi-layer perceptron, which really was just a simple feed forward, one hidden layer or two. I tried it with two. Ultimately, it worked better with one hidden layer and an output layer, a softmax output layer, or in this case, logistic output layer. So just a little bit about some of the tools I used. I did this in Apache Spark, mainly because this data is probably small enough I could do it on a single machine, but what I did was I built it out on Spark so that it scales easily, because the data is just getting bigger by the day. So I expect probably in another 2 or 3 months' time, this is something we really truthfully need at least a 3-machine cluster for. So ultimately, once we have the word vectors, we can use the amount of the transaction, we can use the financial institution ID, we can use timestamp ID. For example, did the transaction occur in the morning, evening, or did it occur by hour or by day? All of those things you can use. What I ultimately used was just the amount for the first iteration, the amount and the actual vectors themselves. And just so you know, because there's multiple words in a row of data, I just take the centroid. So each word gets a vector, and I just take the average of those, effectively, the arithmetic, think of it as the centroid in the vector space. I did a fivefold probably overkill, but I did a 5-fold grid search using cross-validation. And then I also tuned parameters both for the models but also on the word2vec model as well. And the key thing to tune on the word2vec model is the number of latent dimensions. So these are just some further notes that I made. Corpus has to be large for this really to work well. You need a lot of transactions. Luckily for us, that wasn't really an issue. We had a lot of transactions. I didn't do any subsampling. For those of you that are familiar with word2vec, it's really common to subsample frequent words. This is just, you want to downweight words like to and from and the, things like that. I found that subsampling reduced performance. And I think that's, words like to and from were highly informative. There were a lot of other, what would be considered stop words in most NLP projects were actually informative words in our project, at least reasonably informative. So ended up not even doing any subsampling. So then we just take the centroids, and then further features. So like the next iteration, and one thing, I've done one iteration of this, but haven't really tuned it, whereas you actually take the time and look at the temporal aspect. Because like I said, one of my ultimate goals is to build state space modeling around this. I'm going to talk briefly just about, for those of you who are familiar with neural nets, I don't know if you've done anybody here's done like distributed neural nets, but distributing a neural net causes a lot of headaches. You really only want to do it when you need to. There's several issues related to parallelizing. So basically just, there's different approaches to parallelizing. You can take, you can copy all your nodes to each machine, and you can basically learn subsets and then average your weights afterward. Or another option is to actually send partitions of your nodes. So send some of the nodes to one machine, some of the nodes to another machine. We did the former. Basically just did a copy of node on each machine. And then, once you've done that, you can average your weights afterward. There's issues around that. Definitely you take a hit in performance when you start distributing the neural net. And some of that has to do with the loss function. You can imagine the topology of your loss function is going to vary as you start taking subsamples. And sometimes merging those and updating those at the right time is a tricky matter. It doesn't always work how you think it will. I mean, I've seen, I've done 2 iterations with the exact same settings and have one come out really nicely and the other one just spit out garbage results. So just really, this is the little chart of our flow here. So we just tokenize, we vectorize the words, train a classifier, evaluate, then tune. And when we tune, we both tune the word vectors and the classifier, then classify again, and then evaluate. Right now we're developing labels, so this is ultimately, what I'm presenting here is a binary classifier, but ultimately this is actually like there's 18 classes that we're classifying. But initial results for now are just on the binary classifier. So logistic regression got us 86%. The boosted trees got us 88, as well as random forest got us the same result. The multi-layer perceptron with a single hidden layer got us 94. So that actually surprised me. I think with a good feature space, I would expect boosting and a single hidden layer neural net to give comparable results. So that kind of surprised me, but I think it hints that there's still optimization on the feature side, on the word2vec side that we could do. So we can probably improve that a little bit, is my guess. Some of the further encoding, this is for some of the other modeling that I've been thinking about and some of the stuff we're building out. So one of the things we're working on now is, it's not an LSTM, it's a simple hidden Markov model that takes in this data. It looks for changes of state. And so right now we just have 2 states. One is like building wealth versus depleting wealth. So we want to separate the people who maybe they're good with their money and then they stop being good with their money and then they go back to being good with their money. We want to be able to detect that. So that's one of the things we're working on. I'm going to try and speed this up because I think we're running out of time. Here's some resources that I used. I mostly spent this in, I got a lot of help actually from Adam Gibson at Deep Learning at SkyMind, who's behind Deep Learning for J. And I'm not a Scala programmer, I mean a Java programmer. I've been programming in Scala. My background is more in C++ and Python, so all of that was new to me. But I did find that their library is easy to use, even if you're not a Java guy, or a Java person, sorry. So yeah. SparkNet has a great utility. I didn't use it for this, but I did play around with it, and I found that it was, it's got potential. I thought it was useful, especially for distributed computing, because ultimately everything I did here was on a distributed system. So yeah, that's it. That's the talk. So if anybody has questions.
Thanks a lot for being so. One of the one of the last slides you mentioned tuning of the worthiness and also of the, for example, nodes, etc. Have you
The training.
Yeah, the tuning of the parameters. Do you think there's any scope for actually training back into the word vectors at the same time as training the classifier?
So to answer that, yes. You can treat the word2vec as, so let me go back. I have one of these here. Let's look at this one. So imagine right here, let's look at the skipgram model. You have an input, which in this case is a word, outputs. Ultimately, that's, our first layer is really multiple words. It's a sentence. So you can have multiple inputs as opposed to one. So it's not this, it's that with a few more inputs. It's something we have thought about and I've crudely implemented. But ultimately, it's just a neural net, right? So you can imagine that you can learn this. Those outputs feed into another layer and perhaps into another layer, right? So that you could do that with a simple one pass back propagation. I've not really successfully done it yet. I've just played with the idea. I've coded it up a little bit, but haven't actually implemented that. But I do believe that's possible. Yeah. I mean, ultimately, this model and also some of the subsequent models, just to touch on what you're talking about, is I see it as one model with multiple layers. That's one thing I really like about the deep learning architecture and the concept of deep learning is that, I'll turn that back on in a minute. One thing I like about deep learning, the concept, is you can really incorporate many models into one, depending on how you frame it. If you do it properly, I think you can do exactly what you're saying. Not to mention you can do, you can imagine each one of those is a, you could stack those on top of each other and have something like an LSTM, right? Where you have, it's basically a recurrent net as opposed to just, one back propagation, one input to output. The outputs ultimately feed back into another set of inputs, which is just a copy of the first one, right? So, yeah.
All right, this is two parts. Parallelizing between multiple GPUs in the same machine, or GPUs across multiple machines?
So 2 GPUs on each machine. Yeah. I think it's 2. I have to look at I don't even remember because it's on it's our Spark cluster. And it's, I think the instance there's only 2 versions you can get. One has, I think, 8 or 4, and the other one has 2. We have the smaller one, and I think it's 2.
Can you speak to the small difference in methodology to distribute between two GPUs on the same machine and then the conflict of multiple machines?
Not really, because I didn't really even use the GPUs. I did, so I used them only just sort of experimentally. But overall, like to get the final result, I ended up not using them just because there were some complications around that and just
Couple of questions. Let me see. So deep learning for J, that's not a distributed computing architecture. Is that right? Or I don't use deep learning for J.
yeah.
So the other question, when I was looking at your data, I was thinking you probably not become very good in using synonyms for some of those text like transaction versus TXN, something like that.
I'm sorry, what was that?
Synonyms
Yeah.
replacement
Uh-huh.
probably would have done much better in.
Well, so to that end, actually, it did excellent. It captured, because of the word co-occurrences, it captures really well synonyms. It does it very well, actually. That's one of the probably biggest strengths of what I've seen Word2Vec doing is, people can say two things two different ways and use different words, but if they mean the same thing, if you have enough data to train your model with, those co-occurrences will tell the model that in that latent vector space that those words mean the same thing. So it actually works very well for that. And that's what I saw, what I was most impressed with is like, for example, when I looked at payday loans, the closest words in the vector space, can everybody hear me? So I was just saying that actually it's the opposite, that it works very well. For example, when I looked at payday loans, and if you look at all the closest co-occurrences, or the closest, words in that vector space, that they were basically, a lot of them were weird encoded words when you looked at them, but when you actually looked at where they occurred, the transactions were payday loan transactions. So it worked very well. Yeah. I mean, most of the time. It's not perfect, but from a modeling perspective, it worked very well.
Deep learning for J.
Deep learning for J. No, it's not distributed per se, but it's a simple matter to do the distribution. Yeah. So you can imagine you can pass a model to one node, pass a model to another node, and Spark makes that really easy. And deep learning for J, just so you know, has some Spark examples on their GitHub repo. So if you just copy those and use that as sort of a baseline or a template, it's really easy to distribute it. Now just be aware, it's easy to code it up and make it run. When you start distributing your neural net, it's hard to get it to work right. Like there's a lot of considerations. So don't be surprised if your model just, takes a big, anyway, you understand. Yeah. Anyone else? I was going to answer you though. In terms of parallelizing the GPUs, my understanding is that you would treat them just each like a node, right? I think it depends how the graphic cards are paired together. Like in a lot of gaming environments, you can treat that like one graphics card, I think with CUDA, but I'm not sure in the Java deep learning for J environment. That's why we weren't able to really do that. Had I done this in Theano or something, there might be a solution to that, but
And maybe that tricks like compressing the float 16 before transferring between nodes and all sorts of stuff.
yeah, lots of stuff like that. We could go down that rabbit hole, but yeah,
So question about classification. So once you get the centroid, after you apply worthiness, so you just put the centroid, the representation as the input for the neural network, right?
that along with the amount of the transaction and some temporal information. Well, in this particular case, there was just the amount of the transaction. So it was all the weights for the word vector, or for the row vector, the centroid vector, and then the amount of the transaction. Normalized in some way, scaled and normalized. Yeah, that's all. And there may be simpler ways to do that, or better ways, but that's a good first pass. Simple, just take the centroid. Go ahead.
Your initial normalization, you mentioned that you moved digits and lowercase, that sort of thing. I was wondering if the experiments that you said would move certain things, like especially digits, seem to be very relevant in the case, replacing those with some sort of placeholder.
Yes.
Digits were
Yes. Exactly. So like I did use I tried playing with now I didn't see any, so to answer your question, I did do that. I didn't see any improvement, but I didn't, it's one of those things when you're at a company, sometimes you iterate on something and if you don't see an immediate result, you just pass it. That was the case. I suspect there's probably more we could do around that, but one of the dirty things that I did do is I just took, every time I saw one of those sequences of numbers, I just did I had a regex expression, and instead of just stripping it out, you just replace it with a token. Yeah, and the token could be like, account number or something, right? I think I just called it ACCT or something. But
Well, some of them would be, there are different representations. They represent different things. Some will be account numbers, some will be.
you don't really know. It's a lot of it.
You don't know.
Most of the time, it's exactly right. We don't know. The point is, it's just a token that represents, whatever that might be. Yeah. And I just let that be anything it wanted. I forget what I called it. But I put in a placeholder there, and this is something I did like 4 months ago, so I don't remember exactly what I called it, but I put a dummy token in there. I didn't see any improvement in the model in terms of the final output, but it makes sense to do that. Certainly, I think, in many cases, those tokens represent an account number. In many cases, they're a store ID. In many cases, in some cases, they're a phone number. And in a few rare cases, they're like social security numbers, which don't ask me how. But I mean, people, in fact, I think this is one out of like, I found one. I didn't look at every single transaction, 80 million or whatever I was looking at, but I found one that literally said alimony payment to the person's first, middle, and last name, their address, their phone number. I mean, it just had everything. And I was just like, wow. Somebody just copy and pasted like a whole bunch of text in there that didn't belong there. But that was like one out of a, however 80 million that I saw. Yeah. Yeah. I hope it was helpful.